For the record, this is the oral history interview of Doug Baney on August 23rd, 2017 at the Computer History Museum in Mountain View, and my name is Gunter Steinbach. Welcome, Doug.
Thank you.
And thank you very much for agreeing to this interview. My reason for contacting you was your involvement in the development of the laser mouse, but the interview is not just about that, it's your oral history, including, well, your life up to now. So let's start with the background. Where did you grow up, your siblings, hobbies?
Oh, I was born in New Jersey. My father was a Marine fighter pilot turned commercial aviator, so he flew for United. And we moved to California because the weather's better at the airport there than Newark, New Jersey. And so we moved out there in 1965. So I grew up for the most part in Northern California, just north of Santa Barbara in the wine country up there. And I was a family of 5 as a middle child. And my mother was a homemaker and also a small business lady.
Okay, and how about, did you start out early with electrical stuff, your hobbies also? Yeah,
sort of. I think my first experience with electrical was with a rock band. I played bass guitar in a band.
Oh, so did I.
You did too? Okay. And I had a Sherwood amplifier, tube amplifier, and it went dead. And I was trying to figure out what happened there. So I took out the tubes, dusted them off, put it together, and it worked. And I thought, well, maybe I know something about this field. And so it started primarily with electronics, with the band, and also later in my high school, I had a class in electronics.
Oh, really?
And so that was a great opportunity to make PC boards and make my own little electronic counters and so forth, because the 7400 series chips were coming out, so I was able to do some things with that. So that was another experience. Then my uncle in the Navy also supported me when I had some electronics that broke, the Heathkit parts, I couldn't figure it out. Sent it off to the ship, and they trained the technicians there on the stuff that I couldn't get working.
To fix your stuff.
Yeah.
Very nice.
And then also very important is I had as part of a special program in high school that we had a mentorship with Hewlett-Packard. So I used to bike up the hill in Santa Rosa, and there a mentor would work with the team. We were about 3 people from the high school, and we were working on the first microprocessors, how to program them in assembly language.
Wow, that's a very nice perk for being around here.
Yeah.
Very good. And you mentioned something about the Vineyard getting you into actually studying electrical engineering and waves.
Yeah, the wave aspect. The bass guitar string, of course, there's a lot of waves there, but the Vineyard, what fascinated me is I had a job where I pretty much ran the Vineyard off season, so I did the tractoring. I ran the cables across the Vineyard. These are the cables that they're big spools. You put on the tractor, and then you tie it at one end of the post, and then you run the tractor. The thing would spin, and you lay out, cable as you went. And you'd have to tack it up periodically with loose tack, and then you get to the other end of the Vineyard. Well, the Vineyard was probably almost not a quarter mile, but it was pretty long, the distance that you'd run these cables. And I shook the cable just to see what it would do, and I watched this pulse, this wave packet go down the Vineyard. It hit one of the staples I had. Part of it reflected, part of it continued. And I said, wow, this is great. I want to study waves. So I ended up going to Cal Poly at the recommendation of a Hewlett-Packard engineer, and I was going to study microwaves because that was the closest I could get to waves. So that's how the Vineyard tied in with my future.
Wow. That's cool. Okay, so you mentioned the study. Let's get your engineering degrees just up front. When and where you got your degrees?
The first degree was a Bachelor's of Science in Electrical Engineering. That was from Cal Poly in San Luis Obispo. Beautiful place, lovely place near the ocean there. And that taught me a lot of practical things, how to build things and electronic engineering behind it. Then I went back to work, which we'll probably talk about later,
Yeah.
and then went to UC Santa Barbara, right on the ocean there, beautiful. Studied microwaves, optics, and acoustics, and got my master's degree there on an HP fellowship. Then went back to work again, resigned from Hewlett-Packard, a company called Serge Dassault. It's a French aeronautical company, offered to pay for my PhD in Paris. So I went off to France, and then I got my PhD there in France.
Okay. What year was that?
That was in 1990, December 19th, 1990.
Okay. All right. So back to your working career, which I guess was mostly at Hewlett-Packard, right?
Yep, Hewlett-Packard, Agilent, and Keysight.
So yeah, that's right. Yeah, Hewlett-Packard and what it turned into. Yeah, start at the start. When did you become an employee, actually?
I became an employee in 1977. I worked in the stockroom. So it was a high school summer job. And,
okay.
yeah.
I was just going to say, you didn't really start from the stockroom to the CEO.
Yeah, no, not CEO. But yeah, I started in the stockroom where I learned how to pull parts from bins really quickly and count them, these little capacitors, little transistors, parts. And there, I pushed a cart around, and as fast as I could, I went through this stack of IBM cards, pulling out part numbers like 1800-0026, capacitor, count out 100 of those little grains, put them in a package, and off it went to the production line. And so I did that for the summer, and that was a great experience because I learned a lot of electronic parts.
Yeah.
Then I had an internship in 1980 in the microwave laboratory at the Santa Rosa division. And there I worked on a new kind of transmission line called a suspended substrate transmission line. And it was designed to propagate waves at millimeter wave frequencies, you know, like U band, V band, W band, so up to 110 gigahertz. And so my job was to build these substrates. I had to learn how to lay out microcircuits and then characterize the dispersion and transmission properties, you know, of these microwave transmission lines. And there I learned a lot about wave theory too in that summer job. And that was in my third year at Cal Poly. And then in the fourth year, I accepted a job offer from Hewlett-Packard.
Okay.
You know, I saw offer. Back then, you didn't look at the salary. It said offer. I said yes. That was it. It was different then.
And this was at Santa Rosa then?
Yeah, Santa
Okay.
Rosa division.
And so you went into the microwave laboratory?
Yeah, and so I had gotten an offer, but actually prior to that, I got a phone call from a guy named Siegfried Linkwitz. He's he's also known in the amateur sound community. And my roommate who went to work for Tektronix said, "Hey, Doug, Hewlett-Packard's online." I go, "Great, I got my offer, right?" And I answered the phone. It was like 8 a.m. sharp. He was German, and he goes, "Doug, I'm from Hewlett-Packard. I have some questions for you." I go, "No." So he had the final interview over the phone. He was asking about the wave theory and waveguides and stuff like that. But I passed, and then went to work full-time in the Signal Analysis Division R&D lab as part of the millimeter wave group.
Okay. So what was your first product that you worked on, or project?
First project, we're working on UV-W band mixers. That's basically a frequency range from 40 to 110 gigahertz. Okay. Military love this stuff. And so the first project, this is what part of it looked like finally, was a local oscillator multiplier. So we take a YIG oscillator, which operated from about 3 to 6 gigahertz, and then put it into this, and this would multiply the frequency up, so when you mix it, you had better conversion loss, more efficiency in the conversion from high frequencies to low frequencies. So my job was basically this box. Starting with the transformer, I designed that. Back then, you did things like that.
Yeah.
Then the power supplies, the ALC loops, the control loops, and also the microcircuit. I designed that. It has this funny shape because it's also designed to go into a module. And so this was a combination of gas FET devices, sapphire, 5 mil sapphire circuits, diplexers, amplifiers, programmable filters, everything is there. And then another amplifier which I designed is not shown here. But this was the hard part, was this circuit right here. Also designed a MMIC that went inside there.
Oh.
The gallium arsenide MMIC.
So that would have 100 gigahertz coming out of it?
So what would come out of this is up to about 20 gigahertz, 30 gigahertz. And that would feed on a high frequency cable off to the mixer. And that mixer then would have an amplified high frequency local oscillator. And then it would only have to multiply by 4 or something like that to get to 110 gigahertz. So that was my first project at
That's
Hewlett-Packard.
pretty comprehensive in terms of
Yeah.
the span of technology.
And I learned a lot back then. For example, on the control loops and stuff like that, ground current effects and so forth, the slightest errors and you'd have hum and so forth. So it was a big learning experience for me.
Wow. So, and then you said you got your master's while you were working at HP?
Yes.
Or did you take time off?
It was time off.
Okay.
So I got a HP fellowship in 1985, went down to Santa Barbara, and I think I was on 3/4 salary. It was a really nice program.
Oh,
And I stayed at Santa Barbara. They had a 1 and a 2 year program. The 1 year program, you take like the PhD qualifying exams, kind of like that. It's an oral exam. And basically you go in and you take that exam at the end of your studies. And literally there's 3 professors behind a desk to say, hello, Doug, go to the chalkboard. And then from there on, it's mathematics all over the board. And so I got the master's there.
Okay. Great. Did you ever consider just leaving to go to another employer?
That's a great question. That thought has come up. You know,
There were times when Agilent was kind of...
Yeah, I had a great manager. One of the reasons why I hung around, a great company, great manager. Steve Newton's a wonderful, wonderful person. However, there is a call to the valley and the startups. And there are times when I had some pretty good offers that I had turned down to work at one turned out to be a massive startup, and then another company that did very well. But I don't regret it. The experiences at Hewlett-Packard and Agilent have been wonderful. But there was the call of the startup. Kind of like wolves howling in the distance, you know, join us.
Yes, I heard that call too.
Yeah.
All right, so, but after the master's you went back to HP, right? And up to when you started to, decided to do your PhD, right? Do you want to talk about what you worked in between that time?
Sure.
After the master's?
So at that time, it was the very beginning of fiber optic communications. And the lasers which drive the fiber optic communications, which drives the internet, weren't well understood. There's a lot of work to do and understand these new kinds of very compact semiconductor lasers. So of course they needed tests. Being Hewlett-Packard, we have to test it, right? And so my job was exploring basically optical discriminators for discriminating the lasers. When you modulate the intensity, which is how ones and zeros are transmitted, you know, ones high power, zeros low power. That's the way the communication systems work. Well, when you make a 1, what happens is that not only does the power level change, but the frequency changes, and it's called chirp. And so we were looking at characterizing frequency modulation under dynamic intensity modulation. So that project led me through a certain path to this device here. This is called an interferometer, and this is a product that I worked on. Actually, it did pretty much the whole thing with mechanical engineers. And what it does is it takes in an optical signal, the laser feeds in, it goes into the interferometer, which basically compares a version of itself with a delayed version. That delayed version could be for like 4 microseconds later. And then that output you analyze with an instrument. Well, it's kind of like understanding the change in a person. If you look at yourself in the mirror today and you compared it to 10 years ago, it's seeing how much you changed. Interferometer is kind of that way. It's a way of looking at the change in the laser. Had a polarization controller, which the first one failed. We put on a robot, and when we tested it by hand, it worked great. But we put on a robot, and after 50 cycles, the bearing seized up, and it ripped off the knob. And anyway, so we learned a lot about robotics at that time. But that was the first, well, between the master's and the PhD, this was the box, and this is the box that made me go to get a PhD.
Oh.
Because inside this box in the detection system, the laser would go in, and the quantum phase fluctuations on the laser manifested itself in the interferometer in ways I didn't understand. Mm-hmm. So I said, well, I have to get more education, understand really what's going on here. So that drove me to get a PhD, was this product. Learn more about how it operated.
So you decided to get a PhD, and this time not on, or HP did not offer to help you?
They didn't because I resigned. But
so you just decided to go off and do this.
They paid for my master's. I wasn't going to ask for money again. And so I just resigned and say, you know, I finished the project, and now's a good time to go get a PhD.
Okay.
So I resigned, and what happened was, before I left, they said, well, what if we paid you half time? Would you stay with us? And I said, yes, of course. And so I ended up staying with Hewlett-Packard.
Okay.
So I went off to France.
And yeah, you mentioned that you had the offer of the PhD program actually being sponsored by Dassault.
Yeah, Dassault. Yeah. Yeah.
How did they hear of you?
My PhD professor, Philippe Gallion, was fairly well connected in France, and so typically the professors look for money. So he said, I have some money from Dassault.
Okay.
Yeah.
All right. And I remember you telling me that, like me, you met your wife in abroad.
Yes, I did. It's kind of strange how life takes you on these paths. You know, what got me to France was the fact that my master's degree was it was in the U.S., and I wanted to go to Australia, but UCSB was a great choice. I said, well, the PhD will be somewhere out of country. I just wanted experience out of country. So I came across a journal, it's called Journal of Quantum Electronics. It was an article written by a professor in France. And I thought, well, this guy, it was related to the work I was doing with the interferometer. I thought, this guy knows what he's doing. He did experiments, so he's not just a theoretician, but he could go across domain. So I'm going to go study in France. So I went in France, and I was dealing with the French authorities on the permit to stay in France, which is extremely laborious. The work I had to go through with the paperwork. Even my professor came to the police station once, arranged for it was an 8 a.m. rendezvous with the police in the 19th arrondissement. Went up there, and it was an 8 a.m. appointment, and I knocked on the door, and there's like a line of 1,000 students long. And I say, well, we don't open till 9. And I just saw a little door open up. I saw his nose, and they said, go away. And at the front of the line was my future wife. I didn't know at the time, but Barbara Rogalska, Basha Baney. I met her there and showed her my little, what's called a convocation. It was a little note showing that I needed to go to the interview at 8. She said, yeah. So I waited at the front line. I met her there. And while I was in the police station, as the French police are trying to pick up on her, I dropped my business card off. I said, I'm new in France. Give me a call. We can meet up. So it started from there.
Oh, cool.
Yeah.
So this was early on in your stay.
Yeah. Towards the beginning.
I met my wife on my second day here.
Oh, okay.
Anyway, so what was your PhD work about?
The PhD was about modeling lasers under dynamic modulation. So these are injection current lasers. When you drive them with current, they're very compact, so they can be really cheap. They're multi-section, which is a new kind of laser that allowed you to adjust the gain of the laser, the phase of the laser, and the frequency of the laser independently. But it turns out when you modulate the laser, it creates a lot of changes in frequency I mentioned earlier and so forth. And so my objective was to understand theoretically and also experimentally how these lasers were performing. So it was an extension of my interest at Hewlett-Packard.
Okay. And all right, so what year did you get the PhD?
1990.
90, right. Sorry.
Yeah,
you
December
told me.
19th, 1990.
After which you returned to HP, right?
Yes, flew out of Charles de Gaulle with Basha, my wife, and there's no one in
So
the airport.
you married her during your PhD?
Yes, we got married in Poland, in a small town called Możdżenie in northeast Poland, and had a great wedding there. Invited the whole town. There are 9 houses in the town. It was a farming community. We had the reception in a barn, and then the marriage was in a 15th century church, a very old church.
Oh.
And so we got married, and then came back through 6 months. Let's see, got married in June. Came back in January '91, and that was during the bombing of Iraq. So the airports were empty, planes were empty. So, and started work at Hewlett-Packard Laboratories.
Okay, so that was at the labs in Palo Alto then.
Yeah. They had offered a job at Santa Rosa and also the labs, and they said the labs might be more interesting for me, with the PhD
With the
and the kind of work
PhD.
that was available. Yeah.
Okay. So now then we come to the projects you worked on at the labs.
Mm-hmm.
Talk about it. Yeah.
Okay. I started out building reflectometers. Those are optical circuits, basically. It seemed like at the time everyone who joined the labs in the optical department had to build an interferometer. So I built my interferometer for reasons. Working with the likes of Wayne Soren, a very smart guy, we developed reflectometers that could measure minute reflections in optical fibers or optical systems down to an optical resolution of the order of 30 microns or so. And we developed this to go out to hundreds of meters. And so it was a way of characterizing fiber optic components. Later, that work, there's a new kind of fiber that came out. It's called a heavy metal Z-bland fluoride fiber. You could propagate light down it, and that fiber had active material in it. It had rare earths doped in it. And I started exploring making lasers from that. So we developed the first diode pump blue laser in a Z-bland fiber. Actually, the world's first orange laser. There's actually orange laser in fiber diode pump was done by that. And that was an accident. I was actually trying for a different color, but it came out orange. That was good enough.
And it's worth the paper, I assume.
Yeah, it was a paper. So we published on the Presidium upconversion laser. The upconversion process is kind of like a ladder. You have to get the higher energies from lower energy pumps. And it's like a ladder. You have one laser that pumps you up to a certain level. The next laser brings you up the ladder again, and then the higher up the ladder, the more energy. So you go shorter wavelength photons, which have higher energy, and you get blue light. You design a laser cavity out of that.
Okay.
And so I used initially liquid nitrogen to cool the laser down to study it. And it was really cool. The vapors coming off the table, and the laser's glowing blue. So later worked with like Bill Chang on non-reciprocal devices. These are optical isolators and circulators. That we produced some really interesting work there, and developed noise figure methods for the new optical amplifiers that run the internet. And so we developed the noise figure theory and measurements, and a lot of the measurements are still used today to measure amplifiers globally. So that was another project that had worked on at Labs. Labs is a great environment for exploration.
Yes, I know. All right, and eventually came the laser mouse, right?
Yes.
So, which is a pretty big step from upconversion lasers and interferometers, and I mean into consumer grade things, which have their very own, very different constraints and conditions. So, what made you do that jump?
You had to jump to the laser mouse? Huh.
Yeah.
A little bit of serendipity. So I was managing two groups as a project manager. One was a telecommunications group where we looked at packaging optical devices. Another was a photonics group where we're looking at instruments. And so on the telecom group, we're doing work with electroholographic crystals, which we turned into add-drop multiplexers, which could steer light around circuits. Well, the telecom crash came, right? 2001, 2002, 90% of the industry lost their jobs. So it was a very serious time. We were cutting back also at Agilent. So it came a time where I had to focus the telecom group, away from telecom because we're all going to lose our jobs. And so we better find something else to do. So it came down to exploring two areas. One was non-contact PC board test. So rather than probing down on the circuit, you do it remotely. And the other, there was a need for optical mice because overseas they're producing knockoffs of our current LED mouse. And because of that, we needed new technology. So the division we were working with at the time, called SSD, said, we need help in optical mice. So I thought, well, we could potentially explore that. We didn't have any good ideas. Or we could do PC board test. And I remember one day Wagi Isaac came up to me and says, well, Doug, what are you going to do? I only had 20% of the information I needed to make a decision, right? PC board, which we weren't sure what we could do exactly there. I had some potential ideas. Or the mouse, potential ideas. You know, we had ideas of maybe using strings to move it around, all sorts of ideas. And I said, oh, Augie, we're going to do laser. Well, I didn't know it was laser at the time. We're going to look at mice.
Okay, so it wasn't the laser.
It was not a laser. I didn't say we're going to look at a laser mouse. We're going to look at mice. So I had these brainstorm sessions, and I took the smartest. All labs is really smart people, but I took the people in my group from the telecom group and my photonics instrument group. I had a series of brainstorm sessions. One, as previously, was on the PC board mice, or PC board test, and then the other was in the mice. And so ideas came out, but there wasn't a clear winner. It wasn't obvious what approach to take. So anyway, I told Wagi, well, we'll go with the mouse. And some of the ideas called literally the laptop computer like a string coming out, using strings and stuff. So it was all over the map with these brainstorm sessions. So folks like Tong Shi, Mark Depew, Ian McAlexander, Greg Van Weergeren, Bob Safranis, all PhD level researchers are contributing to these brainstorms that I held. And so it came down to the decision to go with a mouse, look at the mice. So I posted a big sign on the door, said, can we build a better mouse? I suppose a mouse trap. And we got to work on some of the ideas we had. And so that evolved where it looked like we had an innovation that looked like it was going to work really well. And that was actually, rather than the optical mouse, which uses an LED and kind of looks at shadows, we're going to look at surface shape. And so we developed a technology to look at the surface shape. And it was called Quattro. And so I focused down to a core team, Tong Shi, Mark Depew, Greg Van Weergeren and Ian McAlexander helped out as well. As I had Ian look at laser safety, because with this new idea of surface profile, there's a laser involved. Mm-hmm. And so the laser that we're...
Why does it take a laser?
The spatial quality of the beam is very high quality, mm-hmm. and you need that kind of quality to measure fine shapes and surface detail. And so Ian was looking at eye safety issues, and we learned, class 1, class 2, class 3, what lasers to have. The current laser we had was a Sanyo laser. It was a buried heterostructural laser that produced red light. And that was used in our first brick. It's kind of like this clear plastic brick that we used for the first demonstration. Later I thought, well, given the evolution of the VCSELs, vertical cavity lasers, and the way you can produce this in wafers, I said, team, we're going to use VCSEL lasers. And so we focused on that. So with the larger team then, I boiled it down to a small core team of Tong Shi and Mark Depew. I was a manager. It was a very close-knit operation. And we had a horse, which was our mascot. You know, it's in the picture. So with that core team, we had some successes. A lot of people wanted to join the project from outside the photonics group. And unfortunately, I wanted to keep the team very small because it's a very efficient team. And so with the genius of Tong Shi and Mark, we started producing these mice, laser-based mice.
Now, did you stick with infrared, or did you go to a visible light? I would think visible is kind of preferable, or...
Yeah.
I mean, for not, maybe not for the technology, but for people.
The first laser was a red laser. It was visible.
Okay.
But it turns out that this is the optics here. You can see the leads of the VCSEL right here. The VCSELs are really cheap, and they're operating at 850 nanometers. And so cost was everything with the mouse. So by going with these VCSELs, which were currently produced by Agilent at the time, we could have very, very low-cost sources for the illumination that was used.
Okay.
So, and I like the spatial mode, the mode shape of the VCSEL was a very high-quality shape, which was necessary.
Okay, so I guess you don't have to see it if it's low enough power that it doesn't hurt your eye, right?
And you can always put a 20-cent LED in there if you had to, right, to make it glow, right, which they do.
Well, that's an extra 20 cents.
Yeah, yeah.
Okay, so you didn't do much technical work on that, but you guided your team, I assume.
Yeah, the technical work mostly for me was the general direction that we had to go. Constant, as every manager should do, a technical manager. You flood your team with ideas and you have them help sort through. So the push for me was the VCSEL, you know, the choice of laser. Tong Shi did a lot of the optics, so did Mark Depew. So my technical aspects were mostly on the laser side.
Okay. And so you mentioned you look at the shape of the surface. That means you still have an imager? I mean, you look at an image?
Yes,
okay.
Yes. So the previous mouse was based on LED, and it used an imager. And that was actually also invented by labs, the folks in labs, as you know. And so we took the next step, which is to look at the surface shape instead of the shadow in there. But we used the same imager.
Okay.
And that was great because we're trying to get parts for the project. Now, where do you get parts? Well, Penang's far away. It's tough to get parts in a high volume stream. So we went down to Fry's and we'd buy laser LED mice, rip them apart, and then use the parts. You know, so in the picture, there's actual LED-based mouse there, but we're using laser illumination to measure the whiteboard material that we're looking at. Oh. So the previous LED mouse was it's kind of like they say, as you move forward in technology, you're always standing on the shoulders of other people and projects, and so this stood on the LED mouse.
Okay, that is something, it's new for me. I thought when I hear laser, you would use speckle or interference or something like that.
We looked at all that. Interference for surface profile. We looked at speckle, stay away from that. Ended up looking at specular, which is kind of like when you walk down a hallway, the sheen you see off the floor is specular, as opposed to speckle.
Okay, so how long were you and your group involved in this? Eventually you handed off to the manufacturing, right? And
yes, so started around November 2002, and we started the brainstorming at that time, and developed the Quattro mouse, the brick, which you can see in the picture. Then we entered the Great American Mouse Bake-Off. And so we were one of the entrants.
But who put that on?
Jack Winstrand. Dr. Jack Winstrand put on. He was at the division. He says, we need the best mouse. And so I think 3 or 4 different technologies entered, and ours was one of them.
Okay. Do you know what, were they also labs departments or in other divisions that if you remember, I don't know.
We were not allowed to know about the others.
Ah.
I think one of them might have been from labs somewhere else, and then some were external technologies, but we knew nothing of them.
Oh, so he looked elsewhere, outside of
Yeah.
the company. Okay.
Yeah, outside the company.
Okay.
So we entered the Great American Mouse Bake Off. We won, and then Jack sent me that note that said, Doug, fasten your seatbelts, because it took off like a rocket. You know, you had the large production of the LED mice, and though I liken it to a train. Train's arriving in town, you better hop on it quick, and that's what we had to do.
Yeah.
So working with the division, which was called SSD, Roop Grevel, he was a project manager there. We started transferring the technology, which also meant transferring literally Tong and Mark Depew over to the business unit for a period of time. And it took off quickly. The mechanical engineers got involved, developed the mock-ups from our original brick, and then by August 2004, I think, or November 2004, mass production worldwide.
So 2 years.
Yeah, less than 2 years.
At which point it was out of your hand.
Yeah.
Or
Yeah.
did they come back and said there's something not
Well,
quite
at the
right?
time also, we had major organizational changes, and literally things were pulled apart.
Okay.
But we got the mouse done and transferred over. So like the first units, talk about the volumes, you know. When you have instruments like these, you think maybe 5 or 10, 100 a month would be great. 500 a month would be huge. The first units are like 50,000 units of these things. So, you know, it was big production. So, you know, working with professionals like Jack Winstrand and Roop, you know, it's just like, it's a beautiful transfer.
So how far did your group have to go in terms of doing those real deep down trade-offs that you have to do for a consumer product where the price is I assume, almost everything
Heavy. This is the first laser mouse, the MX1000. Part of the big trade-off, one is
Is
starting.
that a Logitech?
Logitech, yeah.
Okay.
So we transferred to Logitech.
Okay.
And the first thing is the laser, right? You know, the other parts for mass quantities, the imager and so forth. So the selection of laser, a lot of work went into that. Labs, we did that,
Okay.
the selection of laser. Then the optics and the imaging system we designed as well. And it had to be developed in very low-cost plastic. The traditional glass lenses, the spheric lenses that we use in telecommunications, could no longer be used, right? So it was huge. I can't tell you what the prices are because I'm not allowed to say, but cost was everything, and then the timing was everything. We had to hit certain markets windows, and so it had to go extremely fast, but it did, and it also leveraged a lot of the parts that were in the LED mouse.
Right.
And of course, Logitech is king of consumer, right? You know, computer accessories. So, working with a great partner, you know, we transferred it over and they packaged it up. We developed our own packages, but Logitech ultimately developed a shell and so forth. And we were primarily the imaging system, the laser, and all that is what we provided.
Okay, so Logitech bought the engine basically from Agilent?
Yeah.
Okay.
Yep.
But Agilent, but they didn't have, I assume, much control over the engine itself, right?
Logitech.
Yeah.
Logitech, as our end customer, they had a lot of control, but we had developed the technology which they took. But certainly on the development side of the laser mouse, they were not involved in the development of the laser mouse, but they're involved as our customer for our end product.
Okay.
If that makes sense.
Yeah, yeah, okay. All right, and are there now knockoffs of the laser mouse?
I'm sure there are. I haven't looked at the market in a while.
But one would assume that somewhere in China there are
I could do a
knocking
knockoff. I'm sure there are knockoffs of it. Obviously, there's an array of patents that we had developed around this, because it's really new ground. But I'm sure today there's knockoffs of it. But what had happened is, after we had developed this project, transferred it to the division, and so forth, we went through some huge organizational changes, and my focus went away from the navigation. We did, at the same time we're developing the laser mouse, we're also looking at other navigation schemes, which we call triangle mouse. So I was working with Tong Shi, exchanging ideas, and he designed the systems. It was basically a system that would do triangulation by scanning this surface with these laser beams, and they'd be moving back and forth, and actually we could then track objects. That didn't pan out, but this one did. So
I think such systems they have now for virtual reality. My son showed me one.
Oh,
where
okay.
You have beacons in the corners, and they scan, and just the timing when it hits you tells them where you are, that kind of thing.
Yeah, this is done based on retroreflectors and scanners, basically.
Okay, so and Agilent produced the engines, the mouse engines,
Yes.
and then they spun off the semiconductors.
Yeah, we spun it off. It went to Avago, and after that, I don't know where it went.
Okay.
I'm not sure where it is today.
All right, so after the mouse, what came next for you and your team?
After the mouse was the dark ages for photonics and optics.
Still
It was at least 5 years, the hard times. And so during that time, I had a very small group. We worked on optical vector network analysis, optical signal analysis, and also some interesting sensors like surface plasmon resonance sensors, for biological studies. But it was a small team at the time because we had to scale back our activities. But during that time, we developed the groundwork for what later became an optical modulation analyzer. So a lot of the theories that were developed during the tough times came to fruition about 7 years later, 6 or 7 years later. And so today, in the optical networks, you have very complex modulated optical signals flowing through them. And so a device called an optical modulation analyzer lets you to understand the constellations that you're seeing that are being transmitted and the quality of the signals. So the work there did pan out, but it took a few years later until we did that. So that was an important one in the area of optics. And there were some other investigations that we did. At the time also, I had personally, my job title had changed, and I'd moved up to department manager, so I was now contributing at a higher level in the organization.
Okay, and to wider range of
ranging from software, automation software, methods of automating software, to nano measurements, a variety of different technologies, with a larger group and department.
You mentioned also to me earlier that you're now getting into photonics ICs?
Yes.
Integrated photonics.
Yeah, I've been following...
I don't know how much you can talk about it, but...
Yeah, I've been following photonic ICs for a long time. Like during the dark ages, I was following coherent reception technology, optical coherent reception technology, which led to the optical modulation analyzer, because the carriers were using complex modulation schemes. So I was watching that in the committees at the conferences. So that moved on, and then you could see now with the movement of photonics, not only to long-haul metro, but it'll move into the data centers in a big way. And the data centers, of course, the traffic's increasing, pick a number, 30-40% per year, right? They're getting bigger and bigger. So at those kind of rates, the need to transmit information is just extraordinary. They have to plan 10x improvements. And so I decided that it would be a good thing to launch a photonic IC activity, because for I think years prior I was working a lot with universities on photonic ICs, special projects. We published a fair amount. And so I thought, well, within the company, it would be good to start looking at photonic ICs. So launched that effort. Greg Van Weegeren is a project manager in my department. He's hiring in really sharp people, and we're looking at doing some really important things in photonic ICs. I can't say the specifics because that's proprietary, but the golden age of photonics is still, we're just emerging. I guess we're just entering the golden age, which for me is photonic ICs.
That was going to be my next question. Do you see that all coming back after it totally crashed in the early 2000s?
I think around 2003 or 4, when we were really at the toughest time, I said, one of the people in my group said, the golden age of photonics is ahead of us. It's not behind us. Because everyone's looking at how great it was during the boom. So no, the future is ahead of us, and it really is. We're going to go with analog photonic ICs, and that will be around probably for the next, my guess, 2 decades. And then after that, there may be a means of making digital photonic ICs instead of analog-based, and that will be the next revolution.
We'll see.
Yeah, yeah. Check back in a couple decades.
But this, I thank you for this assessment. Yeah. All right. So I guess that gets us to today, right? Can you give some more general insights about working in and managing high-tech R&D and the kinds of people who do that?
Definitely, definitely. I think going into an R&D environment, or actually any environment, as a new engineer, always look at the quality of the people that you're joining. You don't want to be the big fish. Maybe in some cases it makes sense, but normally if you're looking to develop yourself, you want to go in with the brilliant people and work with the best. And in that environment, you learn a lot. You become a manager, and as a manager, it's important to distinguish between applied research and development. And I say as a manager, in applied research, the definition I have of applied research is that when you do a project, it's likely that what comes out was unpredicted at the beginning. In other words, you didn't know in advance how the value came out of it. And so applied research has more of that flavor. You start it with an idea that you're going to get from point A to B. You have an idea, but often the technology you develop expresses itself in other venues, other ways. And so that's a sign of applied research. And so as a manager in applied research, you want to hire people that are smarter than you. Well, for me, it's easy. There's 7 billion people on the planet. Say we're looking for the upper 1%, right? That still leaves you 70 million people. How many are in the profession and so forth? There's still lots of people. Hire the smart people. If you're doing development, you also want to hire smart people. They don't have to be smarter than you, but generally, I think for the innovation, you need really insightful people for applied research. And so, as within Hewlett-Packard and Agile and Keysight, I think we've been blessed that I think we have really smart people. A supportive management structure is important. A great managers, Steve Newton, Wagi, Darlene, just wonderful people that's willing to support applied research. And so that was important as well. And another thing for me is, as much as possible, when you look at potential projects, try to aim for the memorable. What are you going to do today that 10 years from now you'll remember? And so that's another gauge I use when I see project proposals. Is it going to be a memorable transformation? So.
Okay, so a question about the pull or the difference between applied research and development. I found in my field of IC design that we at the labs, because it's so expensive to make it, we had to do a lot of development. My suspicion is that you will be pulled in that too, as your photonics ICs become more complex and more involved to make. Do you see that, or do you think that's still a long way away?
That's a great question. So, I was thinking out loud on that. One big difference with photonic ICs today versus the kind of ASICs that you're referring to is, we might pay $70,000 to do a run, right, on a wafer. And the tool costs, right, the software tool costs, we could probably do for $50,000. And so the upfront costs and the commitment are order of magnitude less than the $500,000 mask or $750,000 mask.
Okay.
So from that aspect, the notion of back planning isn't as critical for photonic ICs today as it is for electronics when you go down to 22 nanometer nodes and so forth. It gets very expensive. That said, it's not unthinkable in the future that photonics could evolve in a way that you have to do a lot more developmental aspects with less risk. I think that that would be the direction, but we're not there yet.
Okay. And do you have a guess of, is it going to be a decade until you get there, or?
I think so, at least a decade.
I think so.
Yeah.
Okay.
Yeah, because photonics, in a way, it's all traveling wave structures, and it doesn't quite have the densities yet that you have with electronic ICs. Things tend to be large. Now, photonic crystals, very small, very microscopic manipulations of light, as that evolves, then densities could increase. And when electronics and photonics combine on a single chip, then you're talking about, you're running a 14 nanometer chip with photonics on it. Yes, exactly. You better do your planning.
And the universities are looking into that.
Yes,
right?
yes.
They do that kind of integration. And I've seen pictures of stacks where the electronics chip on top of the optics and all kinds of things.
So you can do the electronics like at the front end of the process, layer the electronics on there, or the other way. And like the folks at Berkeley did this all in one, right? It's electronics and photonics on a single chip. Today, for performance, it's going to be more heterogeneous structures. There'll be interposers, and you can do the photonics separately. But one day, according to Star Trek, right, you will one day have all this integrated, and the back planning approach, the investments, is going to be quite a bit more.
Okay. All right. So how about outside of work now? I guess we are through your career so far.
Yeah.
Maybe you'll be back in 10 years. I don't know.
Who knows? Outside work.
I found you as an author of science fiction books on Amazon, and I had to look. Is this that Doug Baney that I'm talking to?
The same one? Yeah. I got into writing a little bit. I have 4 kids. One's now at vet school, the youngest in Edinburgh. My son's at the University of Illinois, 2 graduate, 2 girls from UCLA. And when they're young, I used to tell them stories. The problem was when you read stories to kids when you're young, I'd fall asleep trying to read the story. I've read so many times, right? So the only way to stay awake is for me to make up stories. So I was constantly making up stories. At the same time, I was, I think around 1997 or so, I contributed about 180 pages to this book. So I got my first experience in technical writing, learning how to combine mathematics and images and so forth, right, to make a book. And so I had some experience with the book there, and I published a fair amount also in the scientific literature. So I thought, well, I love hobbies, and I wanted to do a hobby, so I started thinking about this story about a professor who's trying to figure out what a photon is. Believe it or not, nobody knows what a photon is. Right? They describe it, they don't know what it is. So I started this series, it's called Boomerang Series, about a professor's investigation of photons, and then the revelation it reveals and so forth. And that came out as a science fiction book. And then I did another one, which was the next one, where bad things happen with artificial intelligence. Right? Classic, classic. And then things happen on Earth from a geopolitical standpoint after the bad things happened with artificial intelligence. So that was interlude. So this series will probably be 5 books. And then I had fun with literature, just fun literature. So it's a story about a Chevy Chase-like family that moves to Canada and has picks out the wrong Christmas tree and the bad things that happen. So it's comedy. So I did get into writing, and I continue it as I have time.
So your readers now know what a photon is?
Haven't figured out yet, or plan to use artificial intelligence to solve that one. It's yeah. Einstein's spent his career at the end trying to figure it out. Nobody's figured out what it is. I was a telling thing is I was at Bell Labs having lunch with some great minds there, like Jim Gordon, famous for the Gordon House effect, Lynn Mollenauer, the Russian scientists they had there, and are having lunch there. And this is how this kind of relates to the story. And we're talking about measuring solitons, a new kind of optical particle that we're thinking they need test measurement equipment for. So I finally asked Jim, well, you've been working with photons for how long? 20 years? Nods his head, and everyone looks at me. I said, well, what is a photon? And then he just stopped, and no one spoke. And he said, well, Bell Labs management says we're not allowed to talk about that. Because they spent, I'm guessing they spent so much time trying to figure out, they wasted a lot of time. Nothing got done. And so at the end of the lunch, finally, Jim says, well, it's that which yields a photoelectron, like a solar cell, because we don't know what it is, but it generates electricity. And so anyway, that sort of got me into the storyline in science fiction, how it started with the professor's investigation. I like music. I mentioned I used to play in a rock band, bass guitar, so I joined a band at work. We were an Agilent band at first, then we became the Splits. When Keysight split from Agilent, we called the Splits. And I played with them for a while, had a lot of fun, but I just ran out of time. And I'd like to compose them myself, but playing covers takes a lot of time for me, trying to understand how to play the different songs. So I left the band, and then when I have time, I try to compose on my own. And so that's how I spend some of my time. Also love astronomy, and so recently went to Madras, for the great eclipse. It was stunning.
Monday, right?
Yeah, it was Monday.
I saw a little bit here, but I'm told it is very different if it's total.
Yeah, for me, if you're in the 99%, 97, 90, down to 80, it's kind of like a metaphor I use like a water slide. You get on a water slide, if you're not in totality, it's like you have a 3-foot drop. Oh, that was nice, right? In the water, you go 3 feet down. That was fun. But in totality, it's like you take that 3-foot drop, and all of a sudden, woof, exponentially, it goes down. You just plunge into darkness. And for me, that was just astonishing. Just how quickly that happened. And I looked up and saw the sky with the eye in the sky with the kind of the flaming white blue colors coming out of it.
You do see that with naked eye?
With the naked eye.
Without a telescope.
I took off my glasses and looked at it in totality. Now you only do that for a few seconds, I think, because if it comes back on, you can damage your eyes. But I did that, and I could see Venus in the sky, the planets in the sky, in the night sky. So it was stunning.
Wow. Okay. Anything else you want to say?
I think we covered a variety of topics. I appreciate the opportunity to tell a little bit about my story.
I thank you very much for coming, and that's a very, very interesting interview.
Thank you. My pleasure.